Okay, in this problem we have a rotating disk, and this disk is rotating about point O. We're asked to figure out what the velocity of A, the tangential and normal components of A are, and we're given that this disk is rotating with initial velocity, initial angular velocity of 8 radians per second, and a constant angular acceleration of 6 radians per second squared. So unlike other problems where A that we've looked at, where A is on the edge of a disk, this time A is somewhere on the disk, and we're told that A is going to be 1.5 feet from the center of the axis that this disk is rotating around. And what we do to analyze this problem is no different than if A had been on the edge of this disk. The equations are still going to hold true, and we're just going to use the distance that A is from the fixed axis instead of the radius of a disk. So if we look at what the velocity of A is, we know we have this equation. We know we have A is going to be the angular velocity times r. We know our tangential acceleration is going to be the angular acceleration times r, and we know our normal acceleration is going to be the angular velocity squared times r. And of course, r is the distance that this point that we're looking at is from the point that we are looking at is from the rotating axis. So r in this case is going to be 1.5 feet. It's not the radius of the disk, but so we're asked to figure all this out after this wheel has turned 2 revolutions. So what are these after 2 revs? And if we just go back and we define what our velocity is going to be this way, this is going to be our velocity. Our normal acceleration, because A is moving in a circular path, it's going to have a normal component of acceleration. It's going to be pointing back in towards the radius of the path it's moving on. And the tangential acceleration is going to be tangent to the point A is at this particular point in time. So after 2 revs, we want to convert revs. We always want to convert revs to radians. So to get radians, we want 2 revs is equal to 1 rev is 2 pi radians. So 2 revs is going to be equal to, the revs cancel out, it's going to be equal to 4 pi. Now, these equations right here are based on a final angular velocity. So since this is rotating with an initial angular velocity and it has a constant acceleration, we have to figure out what the final angular velocity is in order to use these equations. And we know our initial angular velocity is 8 radians per second. We know that our angular acceleration is 6 radians per second squared, and our angular displacement is going to be how far this entire disk turns, and it's going to turn 4 pi. And we're not given anything about time, and we're not given what our final angular velocity is. So because it's rotating, because this is constant, the angular acceleration is constant, we can use these equations we have that are sort of like our kinematic equations for motion in one direction. We have that a final angular velocity is equal to an initial angular velocity plus the angular acceleration times time. A final angular position is equal to an initial angular position plus the initial angular velocity times time plus 1/2 times the angular acceleration times time squared, and a final angular velocity squared is equal to an initial angular velocity squared plus 2 times the angular acceleration times the final angular position minus the initial angular position. And what typically happens is people enjoy using these two equations the most. They're most comfortable and they're most familiar with them. That's fine. You can figure out how long it takes this disk to rotate, and then you can figure out with that time what the final angular velocity is. But since we're not given anything with time, we can also use what we were given and directly apply it to this equation, because we have everything in this equation except our final angular velocity. Now, if we do this, we get the final angular velocity is equal to plus and minus the square root of our initial angular velocity squared. So 8 squared plus 2 times the 6 radians per second squared, our angular acceleration, times this change in angular position. If we call our initial point 0, this just becomes 4 pi. And if we evaluate this expression, we are going to get that the final angular velocity is equal to 14.65 radians per second. So this is the velocity. This is the velocity this disk is spinning at after it has undergone 2 rotations. So with this angular velocity right here, we can use it in this equation for velocity, this equation not for angular acceleration, but this equation for the normal acceleration. So our velocity of A is equal to our angular velocity after it has moved 2 rotations, and that's going to be 14.65 times this distance r, which is the point that we are looking at. The distance from the point is from the fixed axis, so that's 1.5. And our final velocity is going to be 22 feet. Now our tangential acceleration is going to be this angular acceleration times r. Our angular acceleration is 6. Our r is still 1.5. So our tangential acceleration is going to be equal to 9 feet per second squared. And our normal acceleration is going to be equal to the angular velocity squared. So that's 14.65 squared times r. R is 1.5, and this becomes 322 feet per second squared. And this right here, I made a mistake. It's 22 feet per second. So how do we get feet per second? Well, we have this radians per second times a feet. And radians is sort of a dimensionless number. So when we multiply something by radians, the radians just goes away, and we just get the feet. The radians is just going to cancel out. So it just becomes feet per second. And the same things happen with this tangential and normal acceleration. We have a radian per second squared times a feet, and the radian cancels out because it's sort of it's dimensionless, and that's why we just get feet per second squared.